Oh well, this is a video on hand calculations for framed structures and Vierendeel girders. Here's a nice Vierendeel girder from Berlin. This is the first video in a series and will only really make sense when you watch all the following videos which will come, which are attached to this. So the aim of the series of videos is to show how to carry out an approximate analysis of a multi-storey frame and a Vierendeel girder. So good luck. Good luck to me as well. Right, so these hand calcs that I'm going to run through are they're approximate modelling, and they could be used for preliminary analysis or for gaining an understanding of a structure or to sense check some computer analysis output. What's the end point of the series of videos? The end point will be that hopefully we'll be able to carry out the draw a bending moment diagram for a multi-storey building frame and a bending moment diagram for a Vierendeel girder with some confidence. And then how we're going to accomplish that? Well, there are several short videos and we start very simple. This video starts very simply, so please bear with me if the pace is a little fast or a little slow for you. It's difficult to be just right for everyone. There'll be simple examples in each video and we'll move step by step. In fact, here are the steps that we'll run through. So these are the hand calcs. So this video is about a stiff beam frame, but in the future we will cover frames with a constant EI with pinned feet and then with fixed feet, and then we'll look at a multi-storey frame and a Vierendeel girder. Okay. So these calcs are based on kind of year one structures. So if you've completed year one structures at a university, you should be okay with these calcs. I've kept them simple, and the reason I've kept them as simple as I possibly can is because I want people to be confident in their hand calculations. There's no point doing something so difficult that you're not quite confident of the answer. So this is a really nice Vierendeel structure in Germany, in Berlin in fact, and here's a structure in America. It's I just googled this and just downloaded it. You can see that it's a stiff frame, so the lateral stability of the structure is gained through the stiffness of the frame. And here's a detail of the Vierendeel girder bridge in Berlin, and you can see that these connections between the top chord and the vertical internal members are moment connections, and that's because in a Vierendeel girder a load that's transferred at one point is transferred, the load that's applied at one point is transferred to the foundations through bending in the members, a little bit through axial force in the members, and also through shear in the top member and the bottom member, transferring these forces from the point of application to the point of support. Great. So let's now have a look at a stiff beam frame. Now, why have I chosen this? I've kept this as simple as possible so that we can focus on just some kind of ground rules before we make a start. So this portal frame has an incredibly stiff beam, and it has 3 pinned supports and 3 vertical legs, quite slender columns really, especially compared to the beam. With the horizontal force applied at the top of this frame of P, we have to decide how that is resisted at the 3 pinned supports. So the way that we decide that is we consider the stiffness of each of these vertical members, because moments are attracted to stiffness, and the stiffer a member is in a frame, then the more bending moment it'll be attracted to it, and so almost certainly the greater the reaction will be. So in this situation, because each leg is fixed to an incredibly stiff beam at the top, it's fair to say that there is equal stiffness in the supports, in the fixed supports of these columns, whether you're on the outside or the inside of the frame, and that means that we can take this P, this force P, and just split it equally between the foundations. These are equally stiff legs, therefore the reactions are going to be equally divided. There we are, P over 3 for each one. As long as we know the height H, we can now go on and think about what's the bending moment in each of these legs. I'm going to ignore the bending moments in the stiff beam at the moment. Right, how am I going to do this? Well, I'm going to model each leg. So it doesn't matter which leg, let's go for the end leg here. So I'm going to model this leg, I'm going to say it's fixed at the top, pinned at the bottom, and it has a force of P over 3 applied to it at the bottom. So here's the model, there we are, fixed at the top, and there's that leg sticking down, and it has this force of P over 3 applied to it, and the height of it is H. And from the top down to the bottom. There we go. So what's the deflected shape? Well, the deflected shape, this point load here is going to deflect this column, so it's going to deflect like this, so that should be at 90 degrees, and it just moves it to the left hand side. Because of that, I can now think about where is, I'll draw it out in a greater degree now. I can now think about, this is a kind of like more of a model of the cantilevering leg. So I can see that by forcing it over to the left hand side here, I'm going to develop cracks, and here, so this is the tension face and this is the compression face. I'm just making, I know we're going slowly, but I always draw my bending moment on the tension face. And when I draw my bending moment diagram, I'm really interested to know where the tension face is. And in fact, the bending moment is going to be 0 at the end of a cantilever, and it's going to be a maximum of force times distance, so P over 3 times H at the root of the cantilever. So the bending moment is going to be PH over 3. We know that the bending moment is going to start at 0 at the end of the cantilever, because we have this cantilever here, and it's going to be a maximum of PH over 3 at the top. I'm drawing my bending moment on the tension face. It's a point load. There are no loads applied over this portion of the structure, therefore the bending moment diagram will be straight over this length here. So if that's, so now I'm going to draw it on this face, so now I'm going to try and draw a straight line, there we are, and that's my bending moment diagram for the leg. And lo and behold, it's going to be exactly the same bending moment diagram for each of the 3 legs. So P over 3 is the reaction, horizontal reaction, and PH over 3 is the bending moment in each of these legs. So now, just to get into the swing of it, perhaps you'd like to have a go at calculating the bending moments in this frame. It's a very, very stiff beam, and the height is 5 meters, the bay widths are 7 meters, and you can now have a go yourselves, just to get into the swing of it. So I'm going to say in this video, as with all videos, it really is worthwhile having a go with these very simple examples. You'll see that these build up so that you can analyse an entire multi-storey frame fairly soon. Right, here we go. So here's the solution. If you want to pause the video, you can do now. Here's the solution. Great. So now what I'd like to do is just kind of round off this video. So we'll have a look at this. This is my favourite picture of a Vierendeel structure. So we're one step closer now to being able to analyse a multi-storey frame structure, or a Vierendeel girder. Please take time to carry out the exercises in each videos, and thank you for watching.